Good evening, and thanks for coming to attend this talk. Primitives and patterns providing foundational changes to next generation Java types. First disclaimer, next generation is not AI here. Okay, it's more about going back to primitives. So that's why the primitives are there. I'm very happy to see some of the very old faces right from the EclipseCon days. So for those of you who have seen my presentation, the next few slides are just very small changes you would have seen so many times, if you remember. I'm Manoj Palat. I work with IBM. I'm a committer in Eclipse Java development tools, but also one of the project leads in the Eclipse JDT. So we'll come what Eclipse JDT is. How many of you have used Eclipse IDE? Oh, wow. That's really nice. So you see something like this. I'm not sure whether some of you use the dark theme, but if you use the dark theme, you can see so this particular stuff, which is, of course, not sure I'm preaching to the choir, but everyone knows this. It is based on the plugin architecture. There is an Eclipse SDK, and we have the platform, and we have the different plugins, the PD, which glues everything together, and we have the JDT, or the Java development tools. So that's the part which I primarily work on. Not I alone, a lot of this team. So what exactly we do? So if your completion or debugger or formatter, code refactoring, quick assist, you name it on Java, that is given by the Java development tools. We have a disassembler too, and we do release every 3 months as an Eclipse quarterly release. Anyway, what exactly does JDT contain? Java development tools, they provide these features based on 3 pillars of JDT, what we call, that is Java model, DOM AST, and Java search. These details are irrelevant for this particular talk, but the one which is the foundation on which the Java development tools rests upon, these pillars rests upon, that is a bottommost layer, that is the Eclipse Java source to byte compiler. And it is not Java C. I mean, every time you get to ask, so how do you use Java C? No, it is not Java C. It's our own compiler, Eclipse compiler for Java, or ECJ. So if you look at the release page, you see the ECJ release separately. So today's talk is mostly concentrated on this. And how many of you use VS Code? Okay, so that's not a disjoint set. Anyway, right? But have you installed the language support for Java by Red Hat? Oh, you don't use it for Java? Yes. Okay, so the silence, I take it as some use it. So if you are using it, you are again indirectly using my Eclipse JDT, because Red Hat internally uses Eclipse JDT, if you can see that shaded portion. That is to, reinstill confidence that we are still important. Anyway, that is, so what exactly does a compiler do? It compiles, it takes a x.java class, x.java file, and it compiles it into x.class. If it compiles, if it adheres to Java language specification. If it does not align to Java language specification, it throws out an error. So that's all it does. I mean, everything, we all know that. So what does Java language specification give? Different features like records, pattern switches. I'm not going into those details. That will be taken by the next speaker, Brigitte. She will go into details of these patterns. What we are interested in this little top primitives in patterns. It's a preview feature. As everyone know what a preview feature is? Yeah, for those who don't know, it is just that, standard features will remain, and preview features would be like, no guarantee that it will be carried over, or whether it will be cancelled, or whether it will be modified, but it goes through multiple versions before it becomes standard, or they decide to throw it away. At this point, primitives is in the fifth preview is going to come, and this is JEP 530. Java 26 was released, as we all know, a few weeks back. So I'll be talking from the Java 26 perspective. For Java 27, this continues unchanged. At least as of now, the JEP 532 is the submitted stage. So yeah, so when we talk about compiler and Java language specification and the changes, sometimes these changes, see, when the compiler generates a class file, and that class file should adhere to the Java virtual machine specification. And some features would have changes both in the language specification as well as some changes in the Java virtual machine specification. Prior to Lambda, Java 7, we had the invoke dynamic instruction that had come in the virtual machine, but the Lambda came in Java 8, and we had the changes there. We had records, and records was primarily a language specification feature, but it had one small addition in the virtual machine specification. We had to emit code saying that it's a record. So we'll get into what exactly primitive types is, and whether we have delta in language specification or virtual machine specification. So this slide is dated, so the flexible constructor is already a standard feature. The primitive patterns is still ongoing. It's a preview feature. So what exactly is this primitive feature? Primitives and patterns. Two things. We are enhancing the primitive pattern matching. We are enhancing the pattern matching by allowing primitive types in all pattern contexts. We'll see code examples for this. And we'll extend the instance of, not the pattern matching instance of, our classic instance of, and the classic switch to work with primitives. We'll also get to know why these fellows do not work with primitives soon. Yeah, this is taken shamelessly from verbatim from the JEP. It is like, enable uniform data exploration, allow pattern matching to use primitive, provide easy to use constructs that eliminate the risk of losing information due to unsafe casts. I mean, very, very complicated statement, but still. Finally, what does it amount to? For the programmer, it amounts to removing multiple restrictions pertaining to primitive types that impose friction between using pattern matching, instance of, and switch. Pattern matching, instance of, and switch. So these are the three things what we are going to cover. Pattern matching has sub items like instance of pattern matching, switch pattern matching, and record pattern matching. And eliminating these restrictions would make it more uniform, especially from a programmer's perspective. Idea is we are looking at uniform data exploration. So now is your time to get out, but anyway, let's get into the code. Also, did I close? No, I didn't close. Yeah. Now I wanted to compare. I wanted to compare the current one and the preview one. So I have created a project which is called primpat classic, and which would have the primitives disabled. Just showing that so that you are confirmed that I'm not doing anything here. So its primitives is disabled, and in the primpat.preview, the primitives are enabled so that we can do a apple-to-apple comparison on what works and what does not work. Now to the code. So this is our motivation for removing the multiple restrictions. And has anybody coded such a complex instruction? All of us have, right? So what does it mean here? We have an instance of, and where does this instance of come? From the language specification. And this is the Java 26 language specification. So I kind of marked up so that I can impress you, which is the instance of operator. So we are talking about the language, the instance of operator coming from this language specification, which says, forget relation expression, which says instance of is either it's a reference type or pattern, but we are looking at the what this is where this is where the compiler says, okay, I look at the specification, say that this is a very valid statement. Now, when we go back and we look at the class file, what does the class file generate? Class file will generate an in the bytecode will have an instance of. See, it just loads X and then checks whether it's an instance of class. Now, this instance of is of course coming from the Java virtual machine specification, and that is that's here. So it says, so what does it take? It takes an object ref and it takes an index and it returns something. So what does it return? From a diagrammatic perspective, let me just move it here. Sorry for juggling this, but it's like this. You can consider instance of the bytecode something like a machine, which takes an object reference, and which in this case is X, and then it takes a class type, which in this case is Y for us. Then it does some magic and outputs 1 if it is a yes, and 0 if it is a no. So that's all what it does internally. Before you're wondering why this is so complex, let's go to the next one. Something similar. Suppose instead of Y, we change it to integer, not int, integer. That would still be same. So previously, see, we can see it in a different way. We can see that if I is an instance of integer, we can see that is it safe to cast I to this type, which is integer. So that's a question which we are answering. And the class diagram, there is no difference in the class diagram. You can see it says instance of Java like integer instead of Y. No rocket science here. Now, can we start with why is this an error? Can anyone? There's no class. Yeah. I think that's probably very simple question for this audience. Yeah, it is an error because as per the Java language specification, it has to be a reference type. And reference types there are two types, right? Primitive types, int, char, etc., and reference types which are class, anything that's related to class. So int is a primitive type, so it is not a reference type, and hence it's an error. Now, if I want to implement this in the new one, so what should I do? So this is the preview board. The preview board is where we enable the preview, and then so before we get into that, so we are not asking the question whether I can cast this. We are asking the question whether I can convert this I to an int. It's a small difference, but I'm telling whether I can convert to an int. Now, can you tell me what else should change for this to implement? The class file, the bytecode, the instance of operator should change. The instance of operator in the virtual machine is supposed to take an object reference. Now, this is not an object reference; this is a primitive, so it has to change. When you look at the specification change, it says no, nice try. We are changing only the source language specification. We are not changing the virtual machine specification. Now what we do? Any suggestions? Oh, you're going far ahead. So yeah. So see, when we look for a type, when you check in for an object of it can be either true or false. In this case, what is a true value and what is a false value? What can be a false value here? So I open up the, I will open up the machine which we talked about, and in this machine, we are, instead of objective, we are sending a primitive type. And the class type is a primitive type. So this cannot be, there cannot be a false here, right? Because I is always an integer. You agree or you don't agree? I'm not very sure. Okay, so in the case of if it was integer, what could be a false value? Null, right? Now in this case, can there be a null? No. So do we really need that machine? We don't really need that instance of machine of bytecode, right? Can we say that it's always true? We can. So let's see what does it generate? So it generates iconst1. That's all. So that instead of instance of, it just generates iconst1. It's always true, and it returns. Yeah. Again, I'm sure you're wondering why such a job for such a very complex area. So let's get into one more. I forgot which number. Okay, OCX3. Okay. OCX44. Is this fine? Sorry, this is the classic thing. So when I go into the preview board, we allow this. We allow it. We allow short s instance of int. Now, should we allow it or should we not allow it? Sorry? Okay, so we'll just don't bother about the classic one. This is the primitive. So we are allowing it. Oh, there is a clue here. Should not have put that anyway. So so it's a s is short and int is so what's happening here? Can this be false? No. Why? It's a two different data types. Why cannot it be false? Yeah. Yeah. Always. So why the fundamentals behind that is like, I don't know how many of you cricket fans, I think not very many in this thing. So it's like widening the thing. And if you look at the number line, it is like, short will have only -3 to 768 because 16. And on the left, the integer is like quite long. And on the other side, no rocket science. So whatever is short here, it can be represented in int as it is. So there is no problem. It's a widening primitive, and we have to, I think we should be returning 1, right? So anyway, so this is not important. So we have already covered this. So we just look at, oh, this is what you're talking about, the comma, so I didn't realize the comma. So, and if I look at the class, do we get the icons1? We do get icons1. Again, no issues. We are good here. Okay, so before you guys sleep off, let's see. Is this fine? That's always false? That's correct. But it's not always false. No. Okay. Yeah. So but it's saying set and widening primitive. What is the size of int? 32. What is the size of float? Oops. 32, still 32. Size, the storage size. In Java. Yeah, but the key differentiation here is like we call it a widening primitive because of the range of values. Although it's only 32, right? The range representation is huge. Yes, right. So why? Because in IEEE 754, we have the mantissa, which is represented in 23 bits and exponent and blah, blah, blah. So there is a difference. I know I'm taking you back to the college or, old times. So especially in these AI times, maybe it looks so Paleolithic, but, this is the next step is based on this. So we don't know whether it is true or false. So when we say we don't know, we are saying that at compile time, I don't know whether it is whether it's always true or whether it's always false. It can be true, it can be false, depending on the value. So essentially, I cannot emit. Yeah, this is again, not going to go behind these, but these are the different conversions. So let's get back to this x dot float. And essentially, I cannot emit iconst 1 here. So what do I emit? What can I emit in the class file? Yeah, I'll emit this. I load I, and I emit a method call. And this method call is coming from the JVM runtime. So essentially, you're not using the instance of bytecode, but we are using a function, a method which would do the check, which is this function. So you can ignore this. This is a special case, but essentially what it tries is it converts the value first to float and then to int. We are passing int, and then it checks whether it's whether we get the same value or not. If you get the same value, it's true. If you don't get the same value, it's false. As simple as that. But so all these things, the compiler does it for you. It checks what is the type. It decides what exactly is the code that has to be instrumented, and it'll instrument. It's all transparent to the user. And okay. Any guesses? Is this going to be true or is this going to be false? Yeah, we don't know. We don't know. So we have to use our method. So why? Because we are passing int, and it could be a short, and that's this, right? Integer to short conversion. So if it is beyond those boundaries of short, it has to be a false. So same old trick, we put, okay, this class has to be. So we instrument the method. Only thing is the method which we instrument is changed. It is int to short, exact, if it is a conversion. And the definition is more or less the same, so not going into those details. Yeah, I'm closing the rest of the things. Now, what do you think the bytecode would be here? Yeah, that's true. That's all. So the thing is, the byte is signed. Char is unsigned. So they don't agree so they go to a third party, and that third party is this fellow, our integer. So it's not a clear overlap. It's like partial overlap. So first the byte would be expanded, widened to the integer. Oh, no, I think the next one would give it. Yeah, so it'll get expanded to the integer, without any special instrumentation required. At later point of time, that integer would be narrowed to the character. So what's happening is the byte to char is like, first it gets widened and then narrowed, which would mean like you have a byte which is -1, as Jonas said. Yeah, this gets widened with a sign extension. It goes to an int, and then in the int, this -1 becomes, from the int, it goes down to 65535 in the character. Yeah, so that's just the explanation here. Widening to byte to int, then narrowing from int to char. Okay, and one more last thing. I think people are already sleepy, so one last thing. Any takers? What would be instrument here? We are converting Boolean to char. Oh, that's bad. I'm showing the preview part. So it's an error. Why it's an error? Because this depends on something called table of conversions. And here, I'm not sure whether you can see it. So it's not very clear, but let me read it out. Something that looks like equal to is like the identity conversion. So byte to byte, short to short, etc. That's like trivial conversion. Then we saw our integer to short as narrowing. So this thing is called narrowing conversion. And we had the byte to char as widening and narrowing conversion. So this table is given in the language specification. But if you look at the Boolean, there is no, Boolean cannot be converted to anything. So it's an error. So it's like Boolean stays Boolean. It's only identity conversion here. Essentially, there is no change. So you don't think about, there's no change in there's no additions, no new conversions to the language, no change in existing conversions. So you write a code as you were writing earlier, and no change in which conversions are allowed in existing contexts such as assignment. I mean, you don't have to know about this, but how do you know, I mean, how many knows about the contexts? There are different contexts in Java and different rules apply there. So if you look at the context, there is an assignment context. Wow. Yeah, so there is assignment context when you assign something. So there are rules available there. When strict invocation context, when you're looking for a method to figure out which method to invoke. If you don't find that, then there are loose invocation contexts, etc., etc. But something which we are familiar, casting context. When you cast something, then there are rules there. With 22, there was a small section that was added called testing context, which says that when you are doing a type comparison, type and compare, then it comes under the testing context. And there are a set of rules. So not much rules were added at that point in time, but if you look at the JEP for the for this JEP 530, you can see that the testing contexts have a lot of additions and rules listed. So if you're writing existing code, there's no change, but if you are looking at this primitives and patterns, these are the, so you don't have to know about all this. The compiler will flag an error if there is something. Just that it's just there. Now, so enough of these things. Now we are moving to 15 minutes. Okay, so I think this we all know. If it is less than the 24 bits, then we flag float here, the output, and if it is above that, we flag it is inaccurate. So this way you can write the program without any specific type checks, etc. And here, if you notice, we are looking at the instance of patterns. This is how we extend it to the instance of patterns. Same rules, no difference, like what we saw in the instance of types. Okay. Okay, I think I'll have to go into the classic one. So now let us go into the switches. How does the switch look? Let me put it a little simple. If you look at the class file, this is the classic one. If you look at the class file, the switch would be represented by something called a table switch. Everyone familiar with this? Or yeah. Okay. So what is the switch here? So switch here is it is taking an expression I, and then it says case 1, case 2, case 3, right? 3 cases. And if you look at here, table switch says it takes an I. This is the one that it gets consumed, and it will, if it is case 1, it says go to 28. What is 28? 28 is the instruction address, and it says push 100 and go to 46. 46 again is a return, so it returns 100. Similarly, case 2, 33, it says if it is case 2, go to 33, which is the machine address, and here you push 200. It is equivalent to this 200, and then go to 46, which is the return. Simple, no complications here. Now, if I change this to why am I getting an error here? It's a classic one. It's so I'm not sure whether you can read. It says cannot switch on a value of type long, only convertible int values, only which are integer values, like byte, and strings or enum variables allowed. Not even Boolean is allowed. That's more for historical reasons. That's what the internet says, because we have redundancies, we have if then else, we have 32-bit, and unlike C, it's not like you cannot assume that there is a byte is zero. True is 1 or false is 0, something like that. So even for Boolean it is not allowed. For long it is not allowed. Now why? For integer you get case 1, case 2, case 3, but for long it's a 32-bit. It's a 32-bit stuff, so you cannot represent this. So if we are thinking of implementing this in the preview version, how would we do this? Sorry, cast I to int. Yeah. Yes. So you somehow want to change this, map this long to an int, so that we can use the table switch, right? So if we are able to hash map something like 10, 20, 30 to 1, 2, 3, and then you can reuse the table switch. So we do something, in principle, we do something like that. Since we have already a solution for type switches, we kind of reuse that here, and you forget about the line number 4. You see that table switch. It has something. It says 0, 1, 2. So somehow, if you are able to map 10 to 0, 20 to 1, and 30 to 2, then we are good. And how do we map that? So for that, we use something called type switch. Again, it is a built-in function from the JDK, where first we load I. We load I, and we load a constant 0. This constant 0 is the index of this 0. So we say I send I is the long, so that's why it's long, and then then the index 0. And by some magic, this fellow would compare 10, 20, and 30, and will return 0, 1, 2, respectively. But where are we passing this 10, 20, 30? Somewhere we have to pass this 10, 20, 30. Otherwise, how do we get that? So for that, let's go to Believe me, this is the same class file, and here, if you notice, this mechanism of invoke dynamic is out of context for this talk, primarily due to the lack of knowledge of the speaker, and we have this 10, 20, 30 being passed here, and that gets into the call site, and that gets replaced for the invoke dynamic part. And internally, this 10, 20, 10, 10L, 10L, 20L, 30L would be returning. The method will be returning 0, 1, 2 respectively. Is this clear? Or okay. Now, since this is clear, let's. And any questions here? If someone, this is a fundamental change. You don't have to know this. It is just the internal stuff, which is internally happening here. In the compiler will take care of this. Okay, so I'm not going to go into the Boolean because it's like only 9 minutes. Yeah, this also the float also does a similar story. So I'm not going to get into the details. But what I want to show is similar story. If I go to the class file, it'll send a float and it'll send the index 0, and it says, okay, if it is 0, go to 28 and push 100. So which is this 100 if it is 1.0. No change. The type switch will take the float, will hash it to 0 here and return. If it's a default, it'll if it's a default one is 100. Sorry, 300. Now, once I run, what is the output of this program? It is 100. I mean, no doubt about this, right? Because we are passing 1, and if it is 1, it is 100. What is the output of this program? Any guesses? See, you can guess only 2. There are only 2 values to guess. So 300. Okay, let's run that. You think the compiler is an error? Probably. No, it is because 1.0 and 0.999 are float equivalent. So if they are equivalent, then I should have, because you don't know at the calculation time, at the end of the calculation, you might get the float represented 1.0 as 1.0, or it can be 0.9999. So that's the nuance when it is not an integer but it's a float. So in such a case, then I should get a duplicate error here. If I put, because these two are equivalent, this is equivalent to this, so I should get an error. And that's exactly what I get. I get a duplicate case error. Okay, and any questions? No questions. Okay, now going to, I think I have just two more important cases. Okay, I'll skip this. I'll get into something which is more interesting. So now we are talking about type switches. This has been existing for some time, but only thing is now it is a primitive type. And if I go to the class, how does the class look? The class looks a little complex, but you can see that this is a type switch, which takes the status, which takes the status as an input here. It loads the status, and it takes the index of the case 0, and starts from there. So if it is a short, it will return, it will go to 32, the machine code 32, and load the value of short, and if it is not 32, it's the integer value. So no complication here. The same principle, suppose we have now we have a small problem here. The thing is, both are integers. Both are integers, and so you see that the status so far is fine. Invoke dynamic, it's an integer, and then this type switch is capable of only telling that whether it is an integer or not, because we are, if you look at what we are passing the class of the class of this data type. So here we are passing the class of the data type to the it says I, which is the integer class, int class, and it's a type is a class. So it just says what I'm getting is an integer or not. Now how do we, with that, only that capability, we can model only case int I. We cannot model when I less than 10. We can say that it's an integer. Thus we can say with the type switch. So that the compiler will have to stitch here. You send something, it says it an integer, okay, then it says okay 10, I compare with 10, and if the integer compare is greater than or equal to 10, then go to 43. Then here, that means it has to jump to this particular place. How do we make it happen? It goes to 43, I load 1, I const 1, and I go back. There is a loop to the 4. Like I go back and restart, send this value status and check whether it's an integer or not. Now what I do here is, in this case, I start from the index 0, but in this case, I start from index 1. So I just check for data type. The rest of the stitching the compiler does inside the bytecode. And yeah, there is a implicit loop there, but that's how it is. Okay, so I have only 2.5 minutes, so I'll just finish off with just skip some of. I'll finish off to records. Oh, back to motivation. Sorry. Most of us have used records. Oh, yeah. Now, the records, the thing is, you can create a record. You can create a record with primitive types. There is no problem. Still, you're allowed to. But the problem comes when you have a record I, which you have a record which is defined as taking double. You're passing an I and you're creating a record. That's perfectly fine. I will be converted to double when you're constructing that record, because it's a constructor, there's no problem. But when you're taking it out, when you are taking the data out of the record, then you don't get you can get only double. This is actually an error. Yeah, it'll be an error if I show it in the classic. So just believe me, due to lack of time. So we implement this we get this implemented so that the record, when we extract the data, our int I is also recognized, and our double D of course is recognized because the definition is. And if you are really interested in the class file, I am not going to explain it. Afterwards we can get into it. It is like, it again is a type switch, and then it takes an object and then it will go and check use the record extractor, figure it out, and then it will use it will take the double out, and then it will check whether this double can be converted to int. If it's converted to int, then the record r int I will be accepted. If not, you can see this loop, that same principle, it go back to 9, but with an index of constant 1, and then it will return to double. So yeah, I think that's all. So before we conclude, I just wanted to show you the last slide, that is So what we talked about, anything in the white is concept. So testing context, which is something which has come in. We have the exactness concept and the conditional checks. I mean, these are depending on whether, if it is exact, if you just put as 1, and if it is conditional, you put that method. And anything with a black one, these are the features which get implemented. That is the instance of type checking and instance of type, the typical instance of, and switch with all primitives allowed. And the next level, we have instance of patterns, primitives, switch patterns with primitives, and record patterns with the conversion of primitives also allowed. With all this, at the top, you have the uniform data exploration. Thank you, folks. And